Dr. Nathaniel Frizzell, W2NAF, is an assistant professor of physics and engineering at the University of Scranton. Nathaniel's passion for radio and radio science began in middle school when he was introduced to the amateur radio hobby through scouting. And speaking of scouting, Nathaniel, take a look out here in the audience. Take that camera over there. Steve, if you remember Steve Back, WB2OGY from
K2BSA.
Yeah, K2BSA.
Hi, Steve. How are you? Good to see you.
Good to see you again.
Thank you.
So Nathaniel eventually went on to earn his BS in music education and physics from Montclair State University and MS and PhD in electrical engineering from Virginia Tech, go Hokies, working in the Virginia Tech Super Dual Auroral Radar Network, otherwise known as SuperDARN laboratory. Nathaniel founded and now leads the Ham Radio Science Citizen Investigation, or HamSCI Citizen Science Collective. With that, Nathaniel, I'm turning it over to you. It's all up to you.
Thank you very much. I really appreciate it. Nice to be here this evening and nice to meet everyone. I always enjoy giving these club talks. So today I'll talk about HamSCI, the ionosphere from your backyard. So I wanted to start a little bit by reminding people about the connection of amateur radio and space weather. So this is a not to scale picture of the geospace environment. So we have the sun and it gives out a solar wind and carries with it a magnetic field, and that interacts with the Earth's magnetosphere, which is over here. So this is the Earth's magnetic field. So that allows most of the charged particles to flow around the Earth, but some of them do make it into the system and cause the aurora. And all of these field lines are connected down into the Earth, and they actually go through the ionosphere. And this is not a static picture like you see here. There's all sorts of variations. So changes in the solar wind and the interplanetary magnetic field can cause the magnetic field lines to move, and that can actually cause changes in the Earth's ionosphere as well. And so all of that can very much affect our radio signals, because especially our high frequency radio signals, they will be refracted off of the ionosphere. So any changes in the ionosphere will affect our radio signals as well. So one of my favorite examples of this is when I was in Antarctica. I got to go there a couple of times, once in 2014 and again in 2017. And I got to operate the KC4 USV station at McMurdo Station in Antarctica. And so that's located right at this star right here. I'll play this little audio clip for you where you'll hear some CW. At first, you'll just hear my side tone, and then you'll hear the incoming signal. And the incoming signal, you're going to hear a lot of pitch changes. And that's what I believe is due to some sort of auroral or space weather activity. And it really gives you an idea of how dramatic some of these changes can be. So I'll play this and let me know if you can hear it. So I'll play it one more time. You can really hear those pitch changes. And what's happening there is you get as you get some sort of auroral activity, you can get different changes in the ionospheric electron density profile, and that can change the path lengths of that the signals are actually traveling through. And so that shows up as these Doppler shifts. And that's essentially what you're hearing here. And then that's the side tone again. Really neat. So this is just a reminder of how radio signals are refracted off of the ionosphere. And if you have signals between, say, around 3 megahertz to 30 megahertz, what can happen is you can transmit them from one location and they will go up through the ionosphere and they'll get refracted back down to Earth. And here's a case where you have just a single hop, but you can also have more than one hop, and this allows you to go around the globe and communicate to faraway places. So a couple different things can happen here. One thing that can happen is that you can have the ionosphere change its state. So like if you, the ionosphere is caused by ultraviolet light and energy from the sun and X-ray energy causing electrons to be knocked off of neutral particles in the upper layers of the atmosphere. And this creates free-floating electrons, free-floating positive ions. And those are the things that can refract the radio signals back to Earth. So if the sun is there as it is during the day, you get a strong ionosphere, and that can refract higher frequency signals back to Earth. If you have nighttime, you can get a recombination where the electrons find the positive ions again, they can recombine, and the ionospheric electron densities can decrease, and then the ionosphere can't support those high frequencies anymore. So instead, they just escape off into space. In this particular diagram, or this movie that's being played right now, this is what we call a ray trace diagram. So the background colors, those are connected to, or those are a visualization of the electron densities in the ionosphere, going from 0 to about 550 kilometers altitude. And then you can use the computer to calculate where a radio signal should go for a particular frequency. So this is a 14 megahertz signal going through many different takeoff angles. And it's being sent from this station here, and it's being sent, and that one in this model is located in Florida, and it's going up toward a station in Wisconsin. And when you see a red line here, the computer is predicting that the Florida station is able to talk to the station in Wisconsin. The changes that you're seeing in electron density here are actually not due to day and night, although that would be similar. This is actually due to the solar eclipse. So when you see the decrease in electron density right here, that's because there's a solar eclipse going through this particular model. This is modeling the solar eclipse that took place on August 21st, 2017. So I'll talk more about that later. What's neat is that as you go higher in frequency, you get less refraction. As you go lower in frequency, you get more refraction for the same ionosphere. And so this gives us a couple of different things. From an amateur radio perspective, it means that as the ionosphere changes, you have a lot of different options in terms of what frequencies to use to try to communicate to the person you want to communicate to. It means that if you are interested in things from a science perspective, you can look at a variety of different frequencies and see how the communications are behaving on these different frequencies. And then that can be related back to what's going on in the ionosphere through ray tracing models like this. So one of the things I'm trying to do is not just understand how the communications are affected by the ionosphere, but we're also trying to understand, if we look at the communications, what is the ionosphere doing? So that's a main theme here. And so in order to do that, we need to have sources of data. How do we look at the different amateur radio communications that are going on? Well, there are a number of amateur radio observation networks that have been set up voluntarily by different hams. So there's a reverse beacon network, which has automated receivers that listen to Morse code CW around the world. There's a WhisperNet, the Weak Signal Propagation Reporter Network, which is a digital mode that is specifically for testing weak signal propagation paths. And then there's also PSK Reporter, which is a website that keeps track of all of the PSK31 and FT8 signals that are going around the Earth. And you can go to these websites and you can either download the data directly, or you can email the person who operates the website and they'll give you the data. And then you can look at, say, for the past 11 years, the different amateur radio communications that were happening around the globe. And so I started using these to look at different scientific effects that we might, different impacts we might see on the ionosphere. And one of the easiest things to look at is the response to a solar flare. So it happens when there's a solar flare, the solar flare can send out a sudden burst of X-ray energy, and that can cause a sudden ionization of the ionosphere. Now, usually, more ionization is good because that allows higher frequencies to refract back to Earth. But in the case of a solar flare, the X-ray energy will actually cause additional ionization of the D layer of the ionosphere. That's the layer of the ionosphere that's closest to Earth. That particular layer is not helpful to most radio communications, the HF bands, because what will happen is there's actually so many neutral particles there that when the electrons in the D region get excited by radio signals from Earth, they'll collide into a neutral particle before they get to re-radiate, and that will actually absorb the radio energy. So if you get a strong D layer, it will actually absorb the radio signals that you're trying to refract. So this is a figure that I made looking at both the reverse beacon network and WhisperNet data from September 6, 2017. And this is a period where we had two big solar flares. So right around 0900 UT, there was one X-class solar flare. And then again, close to 1200 UT, there was another X-class solar flare. And that's shown right here. Down in these figures, this is the RBN and WhisperNet data. So it's basically number of ham radio spots. So I'm looking in a region over Europe. This is the 10-meter band, the 15-meter band, the 20-meter band, and the 40-meter band. And then over here, this is a time series of those spots. So going from 6 to 18 UT, so a total of 12 hours. And then along the y-axis here, this is the distance between transmitter and receiver, between 0 and 3,000 kilometers. So you can see before the solar flare, there's quite a few communications going on throughout the entire period. And then all of a sudden, the first solar flare hits, and then bang, it cuts out all of the communications. You get a recovery. It actually recovers fairly quickly within, say, 10 to 20 minutes. And then you get the communications back again. And then you get a bigger solar flare. And then all of a sudden, bang, that eliminates the communications again for an even longer period of time. You'll notice too that this dashed line over here, this shows you the solar zenith angle. So when this is highest, that's where it's noon, right at this star located at the center of all of these communications. That's the point where you're going to have the solar flare cause the most effect. If the communications, if you're on the night side when a solar flare occurs, the Earth itself will protect you from most of its effects. If you're located right on the day side, you're going to take that solar flare straight on. So another type of study that I did with the reverse beacon network data was a solar eclipse back in 2017. I already showed a ray trace model of that, but during that same solar eclipse, we ran a solar eclipse QSO party. And this was a contest-like event that was designed to essentially flood the entire United States across the location of the solar eclipse with radio waves, HF radio waves. So you might be able to see the effects of the solar eclipse on the ionosphere and on the communications. So what you're looking at here is a map of all of the stations that participated, all of the CW stations that participated in the solar eclipse QSO party, those are all of the little black dots. So if you were a CW station during the SCQP, you should be able to find your black dot on here. The blue stars are all the reverse beacon network receivers that were listening. And then the colored dots are all the radio spots at the halfway point between the transmitter and the receiver. The reason we pick the halfway point is because we're making the assumption that there's a single hop off of the ionosphere. So if we're interested in the effects on the ionosphere, we want to associate that with the location of where the signal is refracted. This is color coded by the maximum amount of eclipse that occurred for that location. So you can see totality went right through the center of the United States, starting in the Northwest and ending in the Southeast. Here is on top, this is a figure of the actual ham radio data, the observations from the solar eclipse QSO party on 14 megahertz. This is what I call a superposed epoch analysis. And you can see that right at 0 in the middle, this is where eclipse maximum occurred. Minus 1.5 is an hour and a half before the eclipse maximum, and plus 1.5 is an hour and a half after the eclipse maximum. And so you can see is 14 megahertz was going like gangbusters before the eclipse came on. This is the eclipse obscuration curve. So this is maximum here. This is where the eclipse goes away. As the eclipse shadow came on and the ionospheric densities became less, the maximum usable frequency decreased, and the 14 megahertz band shut down, and you got fewer and fewer communications. And then as the eclipse went away and the sun came back, the 20-meter band built up again, and you were able to have communications again. So you can really see the eclipse effects here. We were able to model all of this with the ray tracing I showed you before. We didn't just use any model. We used a special version of what's called SAMI-3, which this is an ionospheric electron density model provided by the Naval Research Laboratory, and they put the eclipse into there. So we used an eclipse version of the SAMI-3 ionosphere, and then we use this FarLap ray tracing program to ray trace, test the communications links between every possible receiver on this map. And then we used a grid of evenly spaced theoretical transmitters, and we tested all the links between those. And this is a simulation that we came up with, the results, and you can see it matches quite well with the actual observations. So that was really nice. So all of this solar eclipse QSO party, this is really what led to the development of the HamSCI, Ham Radio Sciences Investigation Group. And so this is a collective that allows university researchers like myself to collaborate with the amateur radio community in scientific investigations. And we're trying to do this for mutual benefit. So we're trying to do things that both benefit the scientific community and push our scientific knowledge forward, while also helping the amateur radio community. And so our objectives are to advance scientific research and understanding through amateur radio activities. We want to encourage the development of new technologies to support this research. And we also want to provide educational opportunities for the amateur radio community and the general public. And so back when we were able to go to things in person, here we are at Dayton 2017. We all had these white lab coats, and there I am at the solar eclipse QSO party. So, but broadly, what are the science goals that HamSCI is after? We're interested in any scientific question that's of interest to the amateur radio community or to the field of space physics. So examples include the solar flare impacts, which I showed already, geomagnetic and ionospheric storm impacts, internal ionospheric electrodynamics, short time scale, small spatial scale ionospheric variability, and also connections with the lower atmosphere. And this is one I'm particularly interested in right now. And so a little bit more in depth, we have ionospheric frontier topics. So these are topics where, the ionosphere has been studied for, 100 years now. but there are still many things we don't know. And some of the places where we are really trying to advance our knowledge is understanding coupling from above versus below. So far in this presentation, I talked a lot about how the ionosphere is impacted from above. We know that we showed you that solar flares can cause these radio blackouts. I showed you that you can get this auroral activity that causes these Doppler shifts that you hear. We know that geomagnetic storms can also create effects that we see in the radio propagation. But we're also learning more that terrestrial weather from the neutral atmosphere from below, can also cause effects on the ionosphere. And so that's actually a big part of what I'm looking at in my current traveling ionospheric disturbance research, which I'll talk about in a few minutes. We're also interested in weather versus climate. We have a fairly good understanding of ionospheric climate right now, meaning that we know there's an 11-year sunspot cycle or solar cycle. We know that there's a diurnal variation. So we know that there are seasonal variations that affect the ionosphere. So all of those are longer term variations that are considered climate, but we don't necessarily have a really good understanding of ionospheric weather. What's going to happen 15 minutes from now, an hour from now, in the next 3 hours. So trying to understand that is a big research topic in the field of ionospheric physics. So how do we make progress? Well, there's a number of different ways. One of the ways I'm looking at is I'm trying to look at the connection between, again, not just from space, but from the lower atmosphere. So I'm interested in how effects in the atmosphere from, say, the stratosphere, the mesosphere, or the thermosphere, the neutral part of the atmosphere, might affect the ionosphere. And in addition to what's coming in from space. And so the thing that I'm primarily looking at the moment are these things called traveling ionospheric disturbances. And these are quasi-periodic variations of your F region electron densities. And so you can break this up into medium scale traveling ionospheric disturbances and large scale ones. And these are often associated not simply with things from space, but these are associated with atmospheric gravity waves. So meaning if you have some sort of wave in the neutral atmosphere from below, that can actually couple with the ionosphere to create these traveling ionospheric disturbances. Now, how does this affect amateur radio? Well, it's possible that you as an amateur radio operator may be able to experience the effects of these traveling ionospheric disturbances. They would appear as if you're on HF radio and you're hearing a particular place in the world coming in strongly, and then they fade out QRM over a period of about 15 minutes to an hour, and they come back nice and strong like 15 minutes to an hour later. That could be a traveling ionospheric disturbance coming overhead. And so here's a simulation that helps to illustrate that a little bit more. This is using an ionospheric model called the International Reference Ionosphere. This is a climatological model, empirical model that's fairly smooth. But I took that model and I put a sample or an example traveling ionospheric disturbance on top of it. And now this is going to be a ray trace, not of a ham radio, but of a SuperDARN radar, which is located in Kansas. But the SuperDARN radar works very similarly to the ham radio. This is on 14 megahertz, so it's similar to the 20-meter band. And what you're going to see is you'll see these, the traveling ionospheric disturbance move through here and affect the ray paths of the radar down here. So I will play this movie. So you can see here's a traveling ionospheric disturbance moving through. And you can see how it causes the rays to focus and defocus down here. So where the rays are focused, that's like that gives you a higher signal to noise ratio. And where they're defocused, that gives you a lower signal to noise ratio. So you can see as this wave moves overhead, it's going to cause, if you're listening to a particular station somewhere out here, it's going to cause that station to become stronger and then weaker and then stronger and weaker. You can also see here how, in addition to if you instead of staying at one particular place, you can see how the skip distance is oscillating between, say, 1,000 kilometers and 750 kilometers. It keeps moving in and out here. And that's another signature of a traveling ionospheric disturbance. And that's a signature I'll be able to show you in the amateur radio data in a minute. So here's where you can see it in the amateur radio data. So in this particular figure, I took data from the WhisperNet, from Reverse Beacon Network, and PSK Reporter. I put it all into a single plot. I looked at data over the United States for a 12-hour period in November of 2017. And here you can see again on the y-axis, we have distance between transmitter and receiver from 0 to 3,000 kilometers. And then here we're looking at 12 hours worth of time. And now what you can see is you can see this first skip distance between the transmitter and receiver. And you can see it's not a straight line. It oscillates quite clearly here. It has a 2.5 hour period. So that's an actual example of a traveling ionospheric disturbance affecting the amateur radio communications over the United States. So I've taken this and I've also compared it to data from the SuperDARN radar. So SuperDARN is an professional ionospheric research radar network, and they have them all over the world, but there's one located right here, right in Virginia over there. It's called the Blackstone radar, and this is looking northwest over the United States. And so here you can see data from that radar. This is backscatter off of the ground. So it's what we call ground scatter. And you can see the same sort of skip distance undulation right there. You see there and you see there. And that matches that skip there and that undulation there. And both of those large scale undulations have a 2.5 hour period that correspond very well to each other. Some other ways we can see this, another interesting way that you can look at these traveling ionospheric disturbances is actually looking at GPS data. And so if you have a GPS receiver on the ground, some GPS receivers are capable of receiving 2 different GPS frequencies. L1 at 1,575.42 megahertz and L2 at 1,227.6 megahertz. So if you have a fancy GPS receiver that can receive both of those frequencies, you can actually measure the time delay between those 2 signals. And that time delay is a function of the total number of electrons that those signals are passing through. And this is the formula for deriving that. It's just important to know that it's just a function of these frequencies, and then there's some other bias terms and things like that. But this is how you get what's called the slant total electron content. This allows you to get the total number of electrons between the GPS satellite and the receiver on the ground. And we actually have those GPS receivers located all over the United States. And if you go to the MIT Haystack Observatory, they collect all of that data and they process it, and they can give you maps that look like this. So this is from that same day. And so you can see a wave front here where there's a peak, an increase in electron density here. There's a trough in electron density over here. And then there's another peak in electron density over here. And this has a wavelength of about 1,100 kilometers and a phase velocity of about 950 kilometers per hour. And this appears to match the TID that we see in the ham radio data fairly well. The idea here is that where you have less electron density, you're going to have less ionospheric refraction, so you'll have a longer skip distance. When you have more total electron content, you're going to have more refraction, and the skip distance will be shorter. And so you can make a movie where you can compare the two. It's hard to do an exact one-for-one comparison here, but you can see some trends where, again, when it starts to go out in skip range here, you can see more blues, meaning less electron density. And when it starts to come in, the skip distance comes in here, you see more reds, so higher electron densities. And so you can really see this oscillation in both the ham radio data and the GPS data down here. Very soon, we'll see a nice, there's a really clear structure right here of a wave front that's going to propagate southeastward here. There's another nice strong wave front. You can see in addition to those large structures, there's all sorts of smaller scale waves going both southward and northward and east and west, all sorts of interesting structure in here. So you can pull out some really interesting things from this. When I was in grad school for my PhD, one of the things that I had to do was I had to look at these medium scale traveling ionospheric disturbances. I did a climatology of them. I did that using the SuperDARN radars. And what I found was that there were more medium scale traveling ionospheric disturbances in the winter and in the fall, but not so many in the spring or the summer. And I could also see that there was more of a quiet, what we call quiet period. So you can actually show that there were not TIDs during the spring and the summer. So that was kind of interesting because because one of the main theories for what's causing these medium scale traveling atmospheric disturbances is that it would be due to auroral activity or due to space weather activity. But if that were the case, or if that were the dominant driver, why would you see some sort of a seasonal pattern like this? And in my PhD research, I found that this pattern was much better correlated with the polar vortex and middle neutral atmospheric phenomena than it was with space weather. So this was done for my PhD using the SuperDARN radars, looking at medium scale traveling atmospheric disturbances. I now have a student named Diego Sanchez who's been looking at the ham radio data, and he's been looking at the traveling atmospheric disturbances observed just in the ham radio data. And he's actually found the exact same pattern. But this is a little, this is useful because we don't believe that the ham radio TIDs are exactly the same as the medium scale traveling atmospheric disturbances over here. We believe these are larger scale, but they still follow the same pattern. Now, again, prior to this, we expected larger scale to follow more of the auroral activity than neutral atmospheric activity. But this result is again suggesting that maybe there's more to the neutral atmospheric activity affecting this ionospheric disturbance activity than one might have originally thought. So again, you can see that more TIDs occur in October, November, December, January, February, and less occur in the summer. And so it's this TID activity or studies that's really driving a lot of the current HamSCI research. So I've recently just won 2 major grants. One is a NASA grant called Enabling Space Weather Research with Global Scale Amateur Radio Datasets. And this is in collaboration with University of Alabama, and the MIT Haystack Observatory. And so we're working to develop an automated way of detecting these TIDs in the ham radio data. And we're also looking to develop an empirical model for predicting this on 7 and 14 megahertz over the United States and Europe. And this is supposed to come from the RBN PSK reporter and WhisperNet data. Along with that, I have an NSF career grant, which is, instead of looking at it more from a statistical sense, the goal of this grant is to do more modeling, more physics-based modeling, and try to understand what the drivers of this are. So this TID activity is a really important part of the HamSCI project right now. But now all of this RBN PSK reporter and WhisperNet data is great, but it really wasn't necessarily designed for studying space weather. It's an amateur radio tool that we've been able to use for looking at space weather. But can we develop some instrumentation that hams would like to build and or use that would be really geared toward studying space weather? And so that's the idea behind the HamSCI Personal Space Weather Station. So this is a multi-instrument, ground-based device that's designed to observe space weather, both as a single point measurement and as part of a larger network. It's personal because it's being designed such that an individual should be able to purchase one and operate in their own backyard. And for hams, we're also looking to have the Personal Space Weather Station provide information about current radio propagation conditions, both locally and as part of a global network. So how does this look? So on the left here, this is the block diagram of the Personal Space Weather Station. At its core is a software-defined radio that should be able to sample between 100 kilohertz up to about 60 megahertz. And you can, from this, you can get raw in-phase quadrature data, and you can derive all sorts of other interesting data products like HF spectrum snapshots. You can monitor the Doppler shift of standard stations such as WWV, can act as a passive ionosonde receiver. It can serve as an amateur radio monitor. This would have to be disciplined by a GPS discipline oscillator. This will provide a very accurate frequency reference and time stamping. This GPS receiver can also act as a total electron content receiver. We would also have connected to this a computer that would be able to do local data reduction and send the data to a central server. We also have a ground magnetometer. Magnetometers are important because they can sense currents that are occurring in the ionosphere and in space. And there's a very close connection between what happens with the Earth's magnetic field and what happens with radio propagation as well. You're all familiar with, you hear that high KP comes on when there's a geomagnetic storm. KP is measured by looking at the Earth's magnetic field. So we've got the ground magnetometer instrument. We have the ability to add on future instruments such as a VLF receiver, which we're looking at right now. And then all this would go to the internet in a public database. We have a lot of different teams working on this right now. So of course, the University of Scranton is leading this effort. We've got the University of Alabama. We have Tapper and Zephyr Engineering, Case Western Reserve, and NJIT. ARDC is supporting this, MIT, and the National Science Foundation. So here's some examples of data from the different instruments. The Tangerine SDR, this is still in development, but we believe that our goal is to have the Tangerine SDR be able to produce data like this. This was collected with an EDIS N200 software-defined radio. And what this is data looking at an oblique ionosonde located in Chesapeake, Virginia. I was able to receive this using the EDIS N200 at my house in Scranton, Pennsylvania. The Grape Personal Space Weather Station, this is a low-cost version of the Personal Space Weather Station. This is able to see traveling ionospheric disturbances by measuring the Doppler shifts of received WWV signals. So normally you expect WWV to be a straight 10 megahertz signal or a straight 5 megahertz signal. In reality, that's not what happens. There's actually small variations. I'll show you more of that in a little bit. Here's some magnetometer data using the low-cost magnetometer we have. And then here's some example VLF, very low frequency received data. So as I mentioned, there's actually a low-cost version of the personal space weather station and a more robust high-performance version that's being developed. Low cost is called the Grape. And what the Grape does is it basically just listens to the carrier of WWV. You can choose whether you listen on 5 or 10 or 15 megahertz, and it down converts that into audio band, and by beating the incoming signal against a GPS disciplined oscillator. And using that, you can measure Doppler shifts in the received signal. And what happens is, as the ionosphere moves up and down, the path length between WWV and your receiver will change. And that's going to cause frequency changes to appear on your signal. So here's an example. This was taken during that 2017 eclipse again. This is actually the day before. So this is WWV 10 megahertz being received near Milwaukee, Wisconsin. You can see before, at the beginning of the day, you get positive Doppler shifts as the ionosphere starts building up. Things stabilize during the day. You get negative Doppler shifts as the ionosphere leaves at night. And then here, this Doppler swing right here, this is due to a small solar flare. This is actually on the day of the eclipse. So again, you get positive Doppler shifts in the morning. When the eclipse comes on, you get negative Doppler shifts. There's another little solar flare right there. There's the eclipse leaves, you get positive Doppler shifts again as the ionosphere builds up again. And then in the evening, you get your negative Doppler shifts. Here's an example of the traveling ionospheric disturbances observed with the Grape. This was observed in Hampton, New Jersey. You can see these traveling ionospheric disturbances that are being observed. So for the higher performance version of the personal space weather station, this is going to be based around a very flexible software-defined radio, which the Tapper group is calling the Tangerine software-defined radio. And this is going to be FPGA based, and it should be able to receive signals between a few hundred kilohertz and 60 megahertz. And it will have precision time stamping and frequency reference. So this is still very much in development. Unfortunately, we are a little behind in the development schedule right now because of the chip shortage. We're having a hard time getting these Intel FPGAs, but hopefully that will be resolved soon. Why do we need a new SDR? Why not just do something that's commercial and off the shelf? And well, all of the off-the-shelf software-defined radios today, they don't have many of the things we need. They don't have dual phase locked receive channels. They don't have GPS precision timestamping or frequency stability. They don't have wideband HF signal processing and a low cost. And they're not integrated into a system for wide-scale scientific data collection. So we're trying to integrate all of these together. The things that are probably closest to this right now are the Kiwi SDRs, which are absolutely wonderful. I have one here. And also the Edis N200. The N200 is great also, but it's very expensive. So we're trying to combine all of these things together. So here's some more examples of what we hope this Tangerine SDR could do. This is an example of listening to that chirp ionosonde in Chesapeake, Virginia, using the Edis N200 at my house. This is using open source software made by Dr. Juha Virnen called the Chirp Sounder software. And this analysis was done by my postdoc, Dr. Dev Joshi. And so here you can see one-way range offset up in the y-axis, and then you can see it sweep the frequencies down here. And so you can get this oblique ionogram, and you can see the ordinary mode and the extraordinary mode right here. And so these are signals of opportunity that just occur
on the HF bands because different governments are running these stations. And so you can identify these on a Kiwi SDR or other software-defined radio with a wideband waterfall. If you see these diagonal lines that are going through your waterfall, that's most likely a chirp ionoson that you could decode with this software. And so here's the Edison 200 I'm using. And I'm using a Zeta 6 BKW antenna at my house. And this is a little bit more about the Chirp Sounder software that you can go download from GitHub and process it. And this is a movie of how the ionograms change with time. This is where the transmitter is located. Here's where the receiver is located. You can see as you go during the day, the maximum usable frequency gets higher. So you see higher frequencies in the ionogram. You can see the ranges move up and down as TIDs go through. Sometimes you see that the signals are very sharp reflections. Sometimes you get what's called a spread effect, where you get different ionospheric irregularities. And so that's what Dev is looking at right now. He's looking at these cases where you have a spread in the reflections with range in a condition called spread F. And so here's chirp sounder observations. And then here again is Blackstone SuperDARN radar. You can see the radar saw lots of irregularities at the same time that our chirp sounder receiver saw those irregularities. So we're working on that right now. The ground magnetometer that we're working on, this is it right here. It's a very small device. The actual magnetometer receiver, magnetometer sensor is right here, and that only costs less than $20, and which is quite amazing because this thing does have an approximately 10 nanotesla field resolution. And so if you were to get the next level up for a scientific grade magnetometer, you'd be spending hundreds or tens of thousands of dollars to do this sort of work. It's also worth noting that the magnetometer here is orders of magnitude more sensitive than the magnetometer built into your cell phone. And so you need, the trick with this is you can't really expect this to work in a suburban or urban environment. You really need to have it in a rural location far away from things that might interfere with it. And you also need to make sure it's very temperature stable. So what you do is you put it into a PVC pipe like this, and then you want to bury it in the ground for temperature stability. And when you do that, you can get good results. So these are results that were collected by Jules Mady, K2KGJ, up in Hillsdale, New York. And so the bold traces are the ones from the HamSCI ground magnetometer in Hillsdale, New York. And the lighter traces, those were measured by the professional magnetometer in Fredericksburg, Virginia. You can see there's very good agreement. So how can you get involved with HamSCI? One of the best ways to do it is to join our Google group. If you go to hamsci.org and there's a Get Involved tab there, you can join our Google group and you'll be on our mailing list. We have weekly telecons every Monday night at 9 p.m. Eastern. We have a telecon to talk about the Tangerine SDR development. Every Thursday morning at 10 a.m. Eastern, we have a telecon to talk about the Grape personal space weather station and also the WWV modulation experiment. They talk about that sometimes. And every other Thursday afternoon, including this Thursday afternoon at 3 p.m. Eastern, we have a general HamSCI telecon that could be about any topic in radio science. HamSCI, we participate in professional science meetings like the American Geophysical Union meeting and the National Science Foundation CEDAR workshop. We participate in amateur radio conventions, like we go to Dayton, been to Hamcation. We also host our own annual HamSCI workshop, and that will be March 17th through 20th this year. It's actually probably going to be in Huntsville, Alabama. We're working on getting those details solidified right now. So we'll have more announcements about that soon. And we have a close collaboration with Tapper, which of course is an amateur radio electrical engineering organization that's been around for about 40 years. So one of the newest projects we have is being led by Christina Collins, KD8OXT. And there's a group of people that are actually working with WWV to say, what information besides time of flight and frequency measurements can we get from WWV? And so they've actually developed a special waveform to try and get this other information that they're going to have WWV transmit, and we'll have people from the HamSCI community listen to. And this is going to be starting, this transmission is going to be starting on November 15th. WWV is going to transmit the test transmission on minute 8, and WWVH is going to do it on minute 48. And so you too can listen to this. If you go to www.hamsci.org/WWV, you can listen to this. So I think that about wraps it up for the presentation today. I'd like to acknowledge all of the many amateurs and hams who've helped out, the funding agencies, the RBN, Whisper, PSK Reporter networks that have provided data, so many people who have helped out. So I'd like to say thank you, and I'll be happy to open it up for questions.
Thank you very much, Nathaniel. And we got a microphone roving around. I'm sure some people have questions. I will open up with the first question. I noticed that you're doing all your work on 14 megahertz, and I think, was it 7 megahertz?
Mm-hmm.
Okay. And the solar cycle, or the annual cycle, as far as for ESKIP, that usually happens on 6 meters. I noticed there was a complete opposite effect in those charts, that there was like no activity, which you were getting in like June, May, June, July, in that area. So it's completely opposite. Are you planning on doing any of this same type of activity in, say, low band VHF from 10 meters, maybe 6 meters, to see about what kind of effects that also has?
I personally am not, but there certainly are people in the HamSCI community who are looking at that. So Joe Dzekiewicz has done he's published a number of articles in QST and CQ, and he's presented at the HamSCI workshop, and he's looked at VHF work. Jim Bacon over in the UK has done a lot of VHF work. So there are certainly people who are looking at this.
Excellent. All right, we have a first question back here.
Okay, thank you. Yeah, terrific presentation. I noticed on the personal ionospheric station that you had very low frequency monitoring listed as well. How do you handle that in a typical urban suburban environment where the VLF interference is just horrendous?
Honestly, you probably don't. So, and that's one of the advantages of the modular system here. So this particular block got put on because I had a student at the University of Scranton, Jonathan Rizzo, KC3EEY, and his passion was really VLF receiving. So he's been developing this, and I happen to be in a rural location, and many of the hams who are working on this project are in a rural location. So this is really geared more for a rural operation, really, as the same thing with the magnetometer. So yeah, I'd say that some of these things, this is where the modular aspect comes in. Some of these things really aren't appropriate for urban or suburban environments. So those environments might focus more on the HF operations.
Yeah, are you connected any way as far as VLF with the Inspire project that's handled out of Marshall Space Flight Center?
Not at this point.
Okay, it's a good group to get involved with.
That's good to know.
Data.
Yeah, I'm actually starting to talk with more Marshall Space Flight Center people right now. As I said, we're looking at. We were originally going to have the HamSCI workshop in Scranton this year, but a conflict came up with our venue, and so we're not able to have it in Scranton that weekend this year. So we're looking at having the HamSCI workshop in Huntsville and at the U.S. Rocket Center, and we're talking with the NASA Marshall Space Flight Center people right now. So I'm hoping that having the meeting there might open up some more of these sorts of connections.
That would be cool.
It would be really cool.
Totally unrelated. Are you finding any correlations between the ionospheric activity and the propensity of lightning sprites, the cloud to space lightning.
That's also something I have not looked at too much. When I did look at it a little bit in my paper on the September 2017 storms, and I didn't see a strong effect when I looked at it there, but that doesn't mean that there is no effect.
Cool. Well, thank you. This has been terrific.
Thanks.
And just a quick comment as well. It makes me feel like time is really flying by. It just seems like last year that we had that solar eclipse where I went up to Hartwell Lake
Mhm.
4 years ago. So
I know.
counter's like, really? Oh, man. All right. We have another question here. Oh, no, I thought we did for a moment.
I want to highlight one other thing. If you go to the HamSCI website, if you go under projects, Christina Collins, she's this PhD student over at Case Western. She's a real go-getter. The WWV project is one of her projects, but she also has this Eclipse and Festival, Eclipse and Frequency Measurement Festivals project, which is connected somewhat with the Grape Personal Space Weather Station. But she has been looking at eclipses around the world, in addition to the one that we had in 2017. So the next one she's looking at is the one in December down in Antarctica, and she's having hams who are down in that region participate in this. So there's still a lot more eclipse activity going on.
And our next big eclipse in the US, I think is what, 2023, 2024? 24?
Yeah, there's two. There's an annular eclipse in 2023 and a total solar eclipse in 2024.
That's what I want to go back to do the total. I mean, this total this last time, I'm so glad I went to an area that had 2 minutes and 17 seconds. It was incredible. It was more like, I got to do this again. So
I agree.
it was great. So I have to go out to St. Louis, Missouri, or somewhere in that area to be able to go ahead and see it. Any other
Yes.
questions? Well, Nathaniel, we thank you very much. Excellent presentation. I mean, you thought sunspots were just a little piece of what's going on with HF propagation, but this was really a cool scientific project to really look at so much deeper. And I'm sure you just scratched the surface of this. And
Thank you.
we'll be sending you out a certificate of appreciation as well. So everybody, thank you.
Thank you.